through the constituents that we were removing and the things that we're trying to get rid of last week. And one thing that I mentioned that I know that I didn't define real well because I was a little off the cuff last week was BOD. And BOD, like I mentioned last week, is more of a qualitative measurement as opposed to a quantitative measurement. You can't just hold in your hand a bag of BOD. You're not going to get it. So BOD is the amount of air required to stabilize a water, a wastewater. So the higher the number is, the more air you have to put into it to break down the constituents in that water, which is why when we look for 30-30 or 30 milligrams per liter on BOD, 10 BOD, that's a measure of how clean that water is. You don't need that much air to break down what little is left in that. And going to the handout here, this is a page from Metcalf and Eddy's 4th edition. It's one of the main books of the wastewater Bible, Metcalf and Eddy. It's an engineering textbook that any student going through wastewater goes through. It goes through how to design all different types of plants. It's one of the things that I use a lot when it comes to calculations or sort of looking up things that I've forgotten. So if you look down at that second one down there, the biodegradable organics on this table, those are the sorts of things that we're trying to break down that are what make up the BOD number, the things that air is trying to break down. They're proteins, carbohydrates, fats, things that the bacteria are going to eat. We talked about suspended solids, and that is something that you can hold in your hand. You can get a measurement of that. You can weigh it out. You can figure out what the concentration is in that wastewater. When we go through our chlorine contact tanks or any other sort of disinfection, we're trying to kill the pathogens that are in that wastewater. It's E. coli. It's any sort of a bacteria that will be sterilized by either UV or chlorine. Normally what we have to do for permit is E. coli. It's some measure of the amount of E. coli left in the water that they don't want hitting the receiving stream. And the last thing we sort of talked about last week was nutrients when we're trying to remove ammonias, nitrogens, phosphoruses. Those are things that are in wastewater. They help aquatic and plant life grow, and so they help our bacteria grow. We need them in the system, a certain amount in the system, sort of like fertilizer, to help that bacteria or to help those bacteria grow. But we don't want a lot of it going into the wastewater stream, because once it ends up in the effluent streams, now you're starting to feed algae, other things in the ground that we don't want to have happen. So that's where we get big algae blooms and eutrophication of streams, where we put all those fertilizers into a creek where everything is flowing into. All of a sudden, plant life blows up and ends up sucking all the air out of the water, and it starts killing fish. EPA hates that.
Makes it easy to fish, though.
It's easier, better than dynamite.
Is that primarily the nitrogen?
Nitrogen is one of the big ones that scavenges it, and really once those things start, once that algae starts blowing up, it just really it sucks the air right out of the water.
Yeah, and one of the things, I'm sure we're going to do more of these meetings. I mean, this covering process in 2 meetings is not enough.
Okay,
good.
One of the things we'll talk about, I think, is when we talk about phosphorus removal, about how the metal salts that we use bind to those phosphorus molecules, and makes it heavier than the water, so that's where it settles down in there, and that's how we remove it from the waste stream.
So the other things that are found in wastewater that are a problem, and one thing that we're seeing right now specifically, especially with the DebL lawsuit, is refractory organics. We have a lot of organic nitrogen in that waste, and refractory organics are very difficult to break down, and there's not a whole lot of good formulas that you can use that say if you have this much of nitrogen tied up in a specific amount of refractory organics, you will get this type of removal. It's very hit or miss. And then heavy metals, zincs, arsenics, metallica, things that might be in the wastewater. A lot of the times our plants don't have to test for these or remove these. the much larger only thing I would say as far as heavy metals for us is on an industrial application. There are certain levels of those heavy metals that Paul and I have to look out for that may kill or inhibit biological activity. And so when we're looking into an industrial, we have to get some really good numbers off of them to say, hey, can you give us a full wastewater panel? And specifically, we're looking for these culprits that might make biological treatment damn near impossible. So that was just sort of some of the things that are in wastewater, and that sort of leads back to how to get rid of it. Or a bowling alley or a hospital, you know, how many roughly gallons per day we can do for that. The ultimate design comes from the engineer. They frequently ask us for recommendations. We can tell them, hey, this is an estimated sort of thing. However, with new low-flow toilets and the EPA, we don't know what your local government is going to make you put in. But it's normally a pretty good starting point if it's not an existing application. From there, we'll try to determine what the waste strength is. Is it an institutional? Is it an industrial? Is it just a domestic sort of application? So we know what the waste strength that we're going to expect is. Extended aeration is pretty much set up for domestic strength waste. You know, we're not going to go at an industrial waste with an EA plant typically. They're sized for 240 on BOD and suspended solids coming in. And it's based off of basically a 24-hour aeration process. It's a pretty simple thing. On the small ones, you can see there's slight differences, but in general, you just got the two main zones. You've got your aeration tank and a clarifier. So we're going to enter in through our inlet port, either through an EQ tank and flow control box or just by gravity. We're going to spend roughly 24 hours in this tank. It's got to come up and through this aeration tank baffle before heading through that cutout in the wall. That's going to lead it into this hopper bottom style clarifier. Most of this is based on retention time. Like Paul said, with 10 state standards, there are specific clarifier volumes that we're trying to hit, and there are specific surface settling. The surface settling rate is a specific requirement according to 10 state standards. It has to be within a certain number of gallons per day per square foot. And this, am I missing the overflow weir? This overflow weir, no.
That's it.
You had your finger up on the plan view.
I know, I'm just wondering why. Is it not shown in this view?
Yeah, it's down towards you.
Are you talking about the
The
trough?
top view.
Here's your trough. Talking about the trough?
Sure, but why is it shown here? Oh, it's a
Yes.
broken line. It's a broken
It's
line.
broken.
I thought it was heading across this way. I'm sorry.
Yeah, it goes all the way across.
It's
It's just
not shown
broken.
fully in this one. I got you. So we have to look for the volume in the clarifier, the surface area of the clarifier relative to the flow, and there has to be a specific length of weir. This 10 state standard says we have to have based on how many gallons per day per linear foot of weir. They're all stuff that engineering designed Lord knows how many years ago, and that's what all the tables and dimensions that are in those
On
tables
those last
are for.
pages where the table is, where it showed the lengths of the tank and the dimensions and stuff like that. All those tanks are based on 240 BOD, which back when these were all done was pretty standard. What we have found lately, though, is with the low-flow toilets and the low-flow shower heads and the laundry, using far less water, what we're getting is higher BOD levels in less gallons per day. So we do have to take that into account when we are designing our systems. Like in New York, for example, we have to design at 320 BOD instead of 240. So if I was designing, not that we do extended aeration plants in New York, but if I'm designing for a 30,000 gallon per day EA plant at standard 240, but I got to design it at 320, I'm actually going to have a much larger system than 30,000 gallons. I'm going to have probably closer to 50,000 gallons per day. So I'd have to sit down and do that math to figure out how much more wastewater do I need to get myself back down to that 240 to come up and look at this chart?
So with EA, it's an older conventional style process. There's not a whole lot of variation to it. It's very easy to operate for operators in the field. There's not a whole lot you can do to mess them up. They're typically going to get you 30-30 on the way out. You're getting roughly 90% removal of your BOD and TSS. They can be designed for ammonia removal. Typically, we have to increase the retention time. We have to add some air, some extra aeration capacity to do that. But we can get ammonias down to less than 3 or so. That's typical. We're normally asked to do something like that. The way it's sort of like the best system and all the other stuff that we've talked about that are not they're continuous flow type systems. You have your tank, you have your clarifier, and you have a sludge return that's going to pull solids off the bottom and return them to the head of the plant. We run a much lower recycle rate than what we do with the best system. And the other thing with the hopper bottom clarifier is that it requires daily to once every 2 days scraping. So the operator is going to have a big handled squeegee, for lack of a better word, out there, and once a day or once every other day he's going to have to go out, stand up on top here, and shove down the solids that have accumulated on the side of this clarifier. What can happen if he doesn't is because we're not running a very high recycle rate here, that's not it's not a strong suction that we're pulling. And what can happen is as you get solids that start to accumulate in here, like I use brown, as you get solids down in here, as you're pulling, you might get basically a spot here where all of this stuff is here and all of this is here, but this is just going to start pulling clear water, and all of your solids have compacted, and it wormholes, or they call it all different sorts of things. But if your return starts going clear, you better scrape the clarifier, because you're not pulling any solids off the bottom. Everything's just sort of compacted, and you're just pulling out of a well. We're still looking to keep this as an aerated tank. So if you guys remember from 2 weeks ago, we're maintaining aeration conditions above 0.5 milligrams per liter in there. Typically they're going to run 1.5 to 3, somewhere in that range on average. Though the way that we operate an EA plant is a little different than the way that we operate a BESS system, especially when it comes to our controls, because in a BESS system, we're running the blowers 24 hours a day. One of those blowers is always running. And in the EA plant, we still have 2 blowers, but they're going to give each other breaks, and they're only going to run once every 30 minutes, once every hour, once every 45 minutes, depending on what the operator actually sees going on out there. And typically what they're going to do is, what they should do is run their blower through a cycle, whether it's 15 on, 15 off, 30 on, 30 off. At the end of that 30-minute time period when it's been on, take a DO measurement. And it might be 5, 6, 7, whatever it's going to be. At the end of the off period, as long as they're still aerobic, as long as they're still above 0.5, preferably closer to 1, they're doing fine, and they'll run that blower periodically. Instead of being on a 24-hour sort of continuous basis. The reason we can't operate the BESS system that way is because we need that recycle rate to be 24 hours a day. We could conceivably run a BESS system that way if we had dedicated blowers for the return air lifts. And we've done that before. Extended aeration. The pros, sort of like I went through, it's a very easy system to operate. It's technology that's been around for quite some time, works fine for secondary treatment. Some of the cons are it's not set up for biological nutrient removal. You're not going to get much, you're not going to get phosphorus removal, you're not going to get denitrification. So in a lot of the coastal areas where the effluent requirements are going lower and lower and lower, it's just not a viable option anymore. And that's about it. They are they're large. That's one of the other sort of things that it has going against it. For the footprint and the flow, they're big. You know, we're taking 24 hours of aeration versus a BESS system, sometimes even an SBR, and MBRs are much smaller than these are, and they get better numbers. So it's one of those products that I think if we're replacing in kind in the field, we'll continue to sell them, but we don't get very many requests for new EA plants once we see what the permit limits are going to be. But it's one of those ones that was one of the first ones out there to be a package sort of system, and we've been doing it for 50, 60 years, and Lord knows how long they've been out there. So, any questions about EA?
Cool. 2 weeks, we'll talk about the best system.
We can do SBRs, we can do RBCs, we do all kinds of fun
You
stuff.
should do it all.
D-night filters, tertiaries.
For each individual process.
Oh, good. Yeah, I'm good with this and the best. But
No, whatever. I mean, we can. I think we talked about it a little bit last week. We run the best system in a little wider mixed liquor. Typically, an EA plant's going to run in a narrower mixed liquor range. It still might be 2,000 or 2,500 as far as the concentration of solids in that tank. But instead of being run from 2,000 to 3,000, it might only like about 150 milligram per liter swing. So what they'll typically do is they've got a sludge holding tank on here. They'll just crack the valve so that every time the blower turns on, they waste a little bit, and they'll try to find that range where they maintain a consistent mixed liquor in that tank. Anything from an engineering?
I just wanted to
Divide that out by 6. Your clarifier has to be roughly 16,333 gallons. So in order to get that volume, these hoppers had to extend below the pad.
And the hoppers are
67.
hopper bottoms are field welded.
Yeah.
So,
Because other than that, I mean, this whole overall tank is 11 foot high, but once we add this for here, now these hopper bottoms end up being 16 foot wide or something like that, or 16 foot long, high or something like that. And
shoot.
I hit bridges if I ship it that way. So the only reason these things are the way they are, as far as field welding at 24 feet, taking this all off, is so we can actually transport it.
Yeah, wide
It can't. I can't move it all in one piece. So depending on the length of this aeration tank, it's going to get split down the middle. The clarifier is going to be shipped separately, and these hopper bottoms are going to be shipped separately. So they'll get 3 main tank pieces, as long as this is under 64 feet, and then the 2 little caps for that. So when it all gets to the field, they'll set it all down, pull it together. They're going to have to do a continuous weld on the bottom, on the inner portion of the bottom, and then on the end walls, they're going to have to do inside and out welds. We don't worry about the bottom underside of this. We never have it anymore. Munich does the thing where they do the angle, so they pull that together, and so this floor is actually going to be, when they pull it together, you'll have your tanks coming in this way, and they'll have. So when they pull these 2 together, now you've got that, and they'll just weld in here all the way down the line.
And who does that?
Contractor in the field.
Okay.
Yeah, when we're going to sell it, we're talking to the engineers. We'll tell them in our proposal, hey, field welding is going to be required, and I tell them how many linear feet they're going to require, because they're going to have to hire a welder, and I want them to be able to put that into their bid so that they know, hey, we got to have a guy out there that can do 60, 24, 100 linear feet of welding to get these tanks pulled together.
And another thing too, and this is important on our side of it, that and I've made this same mistake too, which is we need to know from the owner or contractor or whoever how much space they have to get these tanks in, because they don't take that into consideration sometimes. And we've had tanks ship, I know you guys know this, but you guys don't. We've had tanks ship where they can't get it to the job site because
They're long.
they're too long and they can't make it around a curve, or in the case of just recently in Trinidad, they had to cut it into fours, literally, and so we had to cut it here and here because they couldn't fit it across the bridge that they were trying to get it to. So, that's something that, we do need to remember to do on a regular basis.
We
is
tell them in our
ask them,
proposal, that access to the job site is y'all's responsibility.
Right.
And I remember, Beaver Lake Estates was a big couple of RBC tanks, and Beaver Lake is middle of nowhere, New York. You're driving down a 2-lane residential road, and you make a left down a little hill into it serves this whole community. It's a Jewish vacation community up in upstate New York. Well, Dave was out there at the job site and said, "You guys got to cut all these trees out. There's this truck when it gets here in a week or two is not going to make this turn." No, we'll be fine. We'll get it done. Don't worry about it. So tank gets out there. Why didn't you tell us? And Dave's like, I told you had to cut these trees out. And they tried to back charge Dave like $16,000 or some stupid thing like that to cut these trees out that he had already told them it's coming. It's big. You got to figure if you've got 60 foot here, maybe 67 coming up. Then you've got a little drop, and then you've got a semi that's probably 20 foot. I mean, you've got 80, 90 feet running down the road, and now you want to ask them to make a turn into your driveway. They need a little bit more room.
Just back it in.
Wow. So the bigger these are, the more difficult they get with shipping.
I'm just curious, but have you guys, because we used to do this with houses, have you ever thought about doing that with a helicopter or something? We used to, because we would rent these Russian
Big Sikorskis.
put them up on hillsides.
I
You've
had
done that
a,
before, haven't you?
what was that? Was it Pilot Mountain? What was the job that I always give Buddy Cox a bunch of crap about? That they just weren't going to make it up this hill. It was in a state park, and Mount Pisgah State Park or something like that. Where they were putting the plant, the road going up was just switchbacks and just 180 degree switchbacks the whole way up. And they were talking about taking this thing up in like almost man sections and field welding it, and it was going to be like a 20,000 gallon per day plant.
Well, we've had them do that on another job where we had to have it all broken down and they had to get it through a doorway.
They had to get it into a door, and in through a man door, and they were taking 4 foot wide, 8 foot long sections, 2 guys on the side,
Wow.
400 pounds worth of steel in, go get another 400 pounds worth of steel.
What was that?
I'm trying to remember. That was a while ago. That might have even been before I started. That might have just been a story that Grandpa. I don't know that it was. I didn't sell it. I don't know. We've joked about helicopters before, but it's one of those things where.
We did have the ones that
very
went to Africa
Well, those guys had to go on planes.
that had to
went
go on planes.
Yeah.
With an
Where
inch
they-
on either side or something like that.
They were putting them on
Inch
military
tolerance.
planes, so they had to be specifically designed to fit
In through the
inside
doorway.
these planes, which they ended up getting turned into houses, I think, didn't
Yeah.
they? They turn them inside
Yeah,
and just
Sun
turn them
City
into
and
houses.
down in Sun City.
When was that? How long
Oh, that was a long
Wow,
time
that
ago.
was
That's
long.
that's
Even before me.
70s,
That's
maybe
pretty neat.
late
That was a
early
long time
80s.
ago.
Joe
There's
Wilson
pictures.
worked
There's
on that
pictures around
one.
here somewhere of them load. Did you find them yesterday of them loading these tanks into the
Cargo
back
plane.
end of a plane? It looks like the plane's either taking a dump or having a baby.
It was the largest haul by airplane back then, is what Joe was telling me.
Yeah, well, probably. Well, I mean, they were huge. I mean, they fit with just.
Just so you know, that's a huge difference.
And they paid cash.
Taking a dump or having a baby.
Oh.
Just
Well,
letting you
I'm sure
know.
He knows that.
I mean.
Yeah, tell your wife that.
Brian, with those angles on the bottom of the tank, does that affect tank volume at all, or is it just,
Mhm.
does it?
Yeah, because we can't. They're not square. If I were to say, okay, I need 20,000 gallons a day, the formula is basically length times width times height times 7.48, and that's the number of gallons in 1 cubic foot of space. So if this tank is 12 wide, 11 high, and 10 foot long, this is not going to give me that actual volume. So in our tables, Paul and I have another set of drawings that shows, okay, if you have if this tank is going to be used for aeration, or if it's going to be EQ, or if it's going to be sludge holding tank, because this water level changes, somebody else has already gone through and figured out, okay, this tank is 810 gallons per linear foot. Or this tank is the same tank, because we don't take into account the bottom 1 foot, because we have to keep that full to keep the pumps cool, is 737 gallons per linear foot. And the sludge holding tank is typically a little bit deeper because we want to overflow back in with the supernatant. That tank is 828 gallons per linear foot. And we have those tables for all of our different widths and heights.
Is that 7.48 for the density of water?
No. That is the number of gallons that will be. If you had a box that was 1 foot wide, 1 foot deep, and 1 foot high, you poured water into it, 7.48 gallons.
Gotcha.
So like I said, when we're trying to figure out the volume here, and somebody would, I mean, you would be able to calculate it out if you took our water level and then took your straight lines and broke this all down into 1 cube and then this.
Or just have AutoCAD do area.
And I mean, you can figure it out fairly easily, but thankfully somebody else has already done that for us quite some time ago.
And we get, like I'm working on a bid for a plant in Louisiana, and the engineer gave us his drawing that he sent us is a square plant.
Mm-hmm.
So, I know my plant's going to be longer than what the engineer requested, so I have to let them know that, hey, you're going to need, if you go with us, you're going to need more concrete because you're going to need more pad space, and you need to make sure that this tank is going to fit in where the engineer drew a square tank. Our tanks are not square, so they have to be made aware of that too.
So are all
and the-
BAs made the same? Because they're a dime a dozen you guys talk about, so they're all made
Ours
different
are.
then.
All the
Every
Purestream
manufacturer
tanks
has their own.
are the same.
Okay.
All the Purestream
Cloud,
tanks have this
Aeroflow.
same tank break right here. All the Cloud tanks,
Okay.
yeah, I know. All the Purestream tanks have
Gotcha.
the same tank break. The Cloud tanks have a slightly smaller tank break, whereas we're a little bit longer. And so technically, when we go up and want to replace a Cloud tank, they're going to have a shorter tank at the same volume than ours because they have a longer straight wall.
Okay.
And so we need to sort of know that's, hey, if you want to replace it with a Purestream tank, your 20,000 gallon per day plant is only 35 foot long, we're going to be 38. So you either have to add concrete pad to the bottom of it or something like that. The reason for the tank design, by the way, and we didn't really cover it, is sort of twofold. One of the strongest structural shapes is a circle. So the more circular we can keep that, the more rigid that structure is going to be from the inside and out. And also, we're trying to get this wastewater to roll. We want it moving. We don't want, once we let that air turn off and things start to settle to the bottom, once we kick it back on, we want all that stuff to get back into a mixed state. So using coarse bubbles, we get big honking bubbles coming up here, and it starts to roll, and it's going to roll off these walls. So that's the other reason for the shape, is we want those big, they're inefficient at transferring oxygen, but they're really good at moving water around. So they have that.
As you
that
see, like in this drawing, we only have diffusers on one side of the tank.
right.
So what that does is the air comes up on this side, forces
And
that
it-
water,
and
and it
starts that
creates
roll.
that roll. Okay. Otherwise, if you just had square walls, you're gonna have to either put these in the center or you're gonna have to have them on both sides.
Mm-hmm.
Do they sometimes have to scrape those walls and things too?
No, usually that.
On those smaller ones, you don't have to. The C's.
The C units. Well,
They're straight
smaller ones,
walls.
they don't even, those are straight walls, but those are such small.
Those are so tiny.
they're cute little 4 foot wide, 6
I
foot
know,
wide
they're
tanks.
cute.
And that's something that we may look at. We're talking about doing the residential sort of thing. Is look at that design, look at some of the other ones out there and see how we can marry those two to get down to like 500 gallons per day and below. Because the 500 gallon per day SC unit, it's still, it's one of these made smaller. I don't know about you, but I don't want one of these in my yard. So I think we need to maybe look
Depends
at
how big your
redo-
yard is, I guess.
Well, I suppose that's true, but I want to take a look at maybe redesigning that for volume and change that a little bit. Anyway,
So would they, Paul,
Or an encased
does
unit
someone make a
in a
square
building.
one? I mean, for that job here, or,
Yeah, we're
Bidding?
going up against a company that makes square.
oh, okay.
and they'll be shorter than we are.
Or-
but-
yeah.
That's how we make our
But will they
tires.
be as good as we?
No, nobody.
Nobody's
Won't
as good
last
as
as
us.
long.
If we were to do that,
Mhm.
are we still capable of saying for the residential sector that we are using the best technology and all that kind of stuff?
This would just be it would be extended aeration. It's the same thing that everybody else pretty much is using in that arena. It's just a small version of an EA plant, typically fiberglass. Now here's
Is
here's
there something we could do though? I'm throwing this out as a
Sure.
brainstorm, just to be able to
well, what we could do, and
market it that way with something in there.
We
that
could
would-
find something to put in there.
we could make a miniature best system out of fiberglass.
See,
You know, and do a small one size fits all 500 gallon per day.
Instead of maybe
you
a
know,
mixer,
best
we could
system.
use a pump. I don't know how we would. I know the reason we use mixers as opposed to pumps in originally is because we don't want to shear the flock.
Right.
But in such a small system, we may be able to get away with a pump as
Mhm.
opposed to a mixer.
yeah.
To do that anoxic aerobic thing, and then we would definitely be able to say that we are.
Because Echo Fluid still does that. Like Echo Fluid does.
Would you have a neighbor bitching because you got a blower running?
We'd use a compressor. You're talking about a tank so small at that point you can use something a
Use
glorified
one of those
like a
little-
glorified aquarium compressor.
Yeah.
You know that would be you're only talking a small diameter tube. You're probably only putting a couple CFM
What were those?
in there.
What were those real quiet, like blower things we had in here that one time? I got a couple of them.
All those regens.
Yeah, the regens.
Regen.
They're a little bit expensive, but man, they're
Well, they're
pretty
quiet,
awesome.
and the problem we had with the regens is they couldn't handle the PSI that we run at. But in a
these they
small,
could.
they could because we're only probably talking
That's
a
interesting.
pound of
Wow.
pressure or something
yeah.
like that.
Those regens are
Through
pretty
there.
interesting.
Yeah.
Pumps in general.
I tell you why. Just this 2 weeks ago, and I was out of town those days. I didn't get to see it. A neighbor of mine, 4 houses down, had to replace his whole unit
Mm-hmm.
from 1972.
Cavitec?
whatever it was. Aerojet Cavitec.
Mm-hmm.
Okay. And, it was concrete and everything back then. But they came out with a fiberglass
Mm-hmm.
that was smaller and, lighter and all of this type of stuff. The thing that blew my mind was